All right, so here's a problem. Got a lot of information here. You can see originally when I thought this problem up, I decided we were going to do not only bending, where I need E and I thought, oh, we'll do axial force 2, A and E. Oh, let's do shear force 2. No. We're just going to stick with bending and axial force, and we're not going to do the rotation part. Let's just do the displacement part. So what am I going to need first?
Reactions.
I'm going to need moment equations for this structure, right? We're doing virtual work. So can I write a continuous moment expression for the segment AB?
Yes.
Yes, I can.
Yes, you can.
Can I write one for the segment BC?
Yes.
Yes, I can. So that's what I'll do. Before we go down that road, let's do AB first. If I cut AB somewhere here, do you want to look on the bottom section or the top section?
Top. The top.
Yeah, I think I'm going to do the top, simply because I don't have to find reactions if I don't want to. And then I'm going to cut this structure here, and I'm going to keep going towards the cantilever end. So I'm going to use this little right side chunk. Everybody okay with that strategy?
So we do have to do reactions.
Do not need reactions for this problem. Now, the previous problem we worked with the frame, we had no choice. We had to include a reaction. But here we do have a choice. Now, these reactions would not be difficult. If you don't like that and you wanted to work the bottom end, you could. I think it would be wise just to work this smaller segment here than this piece here. So let's do the section AB first. So here will be section AB. And I'm going to see if I can draw this. So there's the chunk. At the free end there's my 10 kip force, and that has a distance of 10 feet. Over here, acting horizontally, is a distributed load. And that's half a kip per foot. Now I have to decide how I want to measure this. I'm going to decide to measure it down. And I'm going to call that Y. Because I can. And I think it would be easier than measuring Y from the base up and then having this segment be 20 minus Y. Okay? So if I do that, I can calculate the concentrated equivalent force. What will it be? It will be the area of this rectangle, which has a base of Y and a height of 1/2. So this is going to be Y over 2 is the force. And oddly enough, the distance from the cut to the centroid is the bottom, which is Y, also divided by 2. So now I'll come and I will assume right-hand rule for my sign convention, and I will sum moments at the cut on this free body. Oh, I forgot something. I'm going to assume the moment, in this case, AB. And one thing, caution, in frames especially, it's kind of hard to know what's a positive bending moment and what's not. It really doesn't matter. If you assume this to be your positive bending moment in this structure, when you do the virtual load, you have to assume the same. As long as you keep them the same, it'll all work out. So with that said, let's make sure this structure is in equilibrium. I'll start with that moment. With right-hand rule, what kind of moment is that? Positive or negative?
Negative.
It's negative. About this cut surface, what's the moment created by this force Y over 2? Positive or negative?
Negative.
Negative. So the force is Y over 2, and the distance is Y over 2. That's kind of unique. So I'll just note that that's force and that's the distance. And then I've got this load over here on the far end, the 10 kip, about this cut. Is it creating positive or negative moment?
Negative.
Negative, and that will be 10 kips times a distance of 10. Lots of common stuff going on here. So it looks like the moment in AB is equal to all that stuff, which will be minus y squared over 4 minus 100. And that's a moment, so it will have the units of kip feet. Can I check that anywhere? Can I find any kind of it's harder to check that in a frame, right? Remember, this equation is only good from A to B. Do I know the moment at B? Not off the top of my head. Do I know the moment at A? Well, I need the reaction. So you can't really check it. Now, if you have the reactions, you could plug in y equals 0. I'm sorry, y equal, we're going from top to bottom, y equal 20, and you get the reaction at the base. If you plug in y equal to 0, you will get the moment here at B. So if I do plug in y equals 0, it says the moment is 100. And I think you can see this. If you looked at just the section BC, what would be the internal moment at B for a force of 10 times a moment arm of 10? 100. So it seems to be okay. We didn't do it explicitly, but we got pretty close. So now let's do the next section. That would be section... Oh, I probably should have found the axial force while I'm here. So let's do that. So I'm going to go ahead and put in a tension force for AB. And while I'm here, I'll sum forces in the y direction and try to find the force in AB. That's a tension force. It's acting down, so that would be negative in my sign convention. And what other force is vertical? Also negative 10. So it looks like the force in AB is negative 10 kips. So it says the force in AB is in compression. You look at that. Does that make sense? I think so. So now I can come back. Sorry, I got it kind of jammed in here. So let's look at the section from B to C. I'm just going to do this little end piece. And what do I have at the end? I've got my 10 kip force again. And I'm going to decide to call this distance from left to right. I'll call it x1. I can do that. And I will assume a moment in BC, and I will assume a axial force in BC. So let's find the moment first. So again, I'll assume right-hand rule for my sign convention, and we'll sum moments about the cut, make sure it's in equilibrium. So what do we have here? What kind of moment is BC with my sign convention? Positive or negative? It is negative. And the moment of this 10 kip about the cut, positive or negative?
Negative.
Negative. So it's 10 kips times the distance of x1. So the moment, the real moment in BC is equal to minus 10 x1, and that will be kip feet. Now I can check that one. I know the free end. What's the moment at the free end? 0, and that would be at a distance of x1 equal to 0. I plug in x1 equal to 0. Voila. Now I also know that these two moment expressions should give the same value for moment when I get to B. So looking at AB, that would be a y value of 0, which would be negative 100. And looking at this section I just drew here, that would be an x1 value of 10. I plug in 10, negative 100. So that seems to be okay. So now what do I do? Let's get some virtual stuff. So my virtual frame, what will it look like? Well, it's going to have the same geometry as the original frame. That hasn't changed. This is not conjugate frame. And where do I put my virtual force? Well, I want the vertical deflection at C. C is the end, vertical. I think I'll assume it goes down. This is still A, B, and C. Now, I've already decided when I did my real moments, this is the way I was going to cut the structure up, and these were my free body diagrams. When I do the virtual force, I have to do exactly the same one so they match. So when I come back here, in the virtual frame, and do section AB, since I cut it like this before, I have to do it again. Of course, now I just have my virtual force of 1. Before I assumed that everything varied y, I do that again. I assume my moment looked like that. I'm going to do it again, except this is my virtual moment in AB. I assume my axial force was down, so I'll do the same thing here, except this will be the virtual one. I'll use lowercase f for that. And this has a distance of 10. So that's the same free body. This has the real loads on it. This has the virtual loads, and the reactions are virtual. So I'll use the same equations to find those. So first we will sum the moments at the cut. Make sure it's in equilibrium using right-hand rules. So this moment, this virtual moment, is positive or negative? Negative. And the only thing else on the structure is the virtual load, which creates also negative and has a moment arm of 10 feet. So it looks like my virtual moment in AB is equal to minus 10. Then we can sum forces in the y direction. Make sure it's in equilibrium. I'm assuming up is positive, so both my forces are down, so they'll both be negative. So I'll have the virtual load AB and the applied virtual load 1. So it looks like my virtual load AB is equal to 1. That's it. Now I have to redo section BC. That was a pretty simple little free body diagram, just a little segment to the right that we cut here. We've got our virtual load at the end, 1. We assumed a distance to the cut of x1. Now I assume this kind of moment at BC, I have to do the same here, except that's the virtual moment in BC. I assumed tension for the real axial force, so I'll assume tension for the virtual axial force. I just need to make sure this structure is in equilibrium. So again, we will sum moments about the cut and make sure we're in equilibrium. So I'm using right-hand rule, so the virtual moment BC is positive or negative? Negative. And about the cut, the virtual force creates negative, and it has a moment arm of x1. So the virtual moment in BC is negative x1. And then we can sum forces in the x direction. Oh, I forgot to do that up here, didn't I?
That means 0.
Yeah, maybe that's what it was. So I got the wrong sign convention. So this force is negative. So the axial force is 0. Now on, yeah, that's it. I left it out here, but same will be true there. Sorry about that. So now I have all my pieces. Now I just got to put them together. Let's see if I can pull this off. Let me take this off here. So now the displacement at C, we'll do the bending part first. So that'll be 1 over EI. And we'll do the segment AB. Now remember when we defined that, we defined it from the top to the bottom. So it'll go from 0 to 20. So the first integral is from 0 to 20. And the real moment, if you look on your page, you'll see is y squared over 4 minus 100. And the virtual moment for the same segment is minus 10. And we'll integrate that dy. And then we'll add the piece that I wrote here in x1, which is going to go from 0 to 10. And the real moment, if you look in your write-up, is negative 10x1. And the virtual moment is negative x1. And that'll be integrated dx. And you can see that this negative would make all these things positive. So this whole term is going to be positive. And these two cancel too. So this is all going to be positive. So that means my result from bending will be a positive result, which means, remember, we assumed that our virtual load was down, so it is going down. And we're not done here because we have to add to it what? The axial piece. So the axial piece would be the real force in AB. So here's AB. We have minus 10 for the real force and minus 1. And then in the BC section, we have no axial components. So it'll be the real force, which is minus 10 kips, times the virtual force. So that's real force times virtual force, which is minus 1, times the length. The length of AB is 20 feet, but I'll go ahead and write that as 240 inches. And that would be divided by A and E. So that would be the total. We could sit here and slog through all this, but I think you can see this is not too bad. You guys could probably easily integrate that and evaluate it. Maybe we should. Why not? Maybe this is one we can do. There's not enough time to really start a new problem. So what is this? Let's see. That'll be 10y squared over 4. And you integrate that, you get 10y cubed over 12. That is 1,000. Integrate that, you get 1,000y. And that should be evaluated from 0 to 20. Somebody can work on that. Then over here you just get 10x1 squared, which will be 10x1 cubed over 3. Evaluate that from 0 to 10. And then this will be plus, well, 10 times that is 2,400. That will be kip inches divided by AE. Does anybody get that? I know this one. That's 10,000 divided by 3. That's 3,333.3333. I can't do that one in my head. This would require a calculator and fingers. Oh, someone's doing it. Somebody doing it?
So the first one I got 26,666.666.
For this one?
Yes.
Anybody else get that?
That is also what I got.
Anybody else get that? I need a trifecta.
Yes, I also got.
So what did you get again? 26,666.7?
Yeah.
And we already said this was 3,333.3. It looks like that's going to add up to something nice.
30,000.
Wow.
Yeah.
And this is 2,400 kip inch divided by, oh, that's a plus, not an equal. All right, so we're going to have to handle these separately because you can see they're divided by different things. So I'll do the first part first. You said this was 30,000?
Yep.
So that's going to be 30,000 kips per foot cubed. So let's start doing some dividing. We're going to divide by 29,000 kips per inch squared. Divided by I, ooh, that's big, 1,000 inches to the fourth, and then we have to convert that, right? 1728 cubic inches in a cubic foot. Plus 2,400 kip inches divided by E, 29,000 kips per inch squared, divided by A, 25 inches squared. What's this one? It looks like a little more than 1. 1.6. 1.8. I revised my estimate. Exactly?
Yeah. Well, 1.7. The left side is 1.8.
Close enough. And then what's this guy? I say small.
It's going to say
0.025.
0.003.
Very close. 0.003. Which one is the dominant, I think?
1.8.
Yeah, the bending is way bigger than the... So what's the total if you add them together? Carrying some significant figures along the way?
1.803.
1.803. Well, that's easy enough. That seems reasonable. Again, this would be good enough for me. If you got to this point on the exam, that would be good enough for me. I might allow you, well, not allow you, I might offer you some bonus if you have some free time and you're super excited. Any questions?